Part 1, the image Fourier transform pair. For every image, there is a unique Fourier transform. We take this image and run it through our Fourier transform machine, and out pops the Fourier transform. The coordinates of the image, x and y, are measured in radians. The corresponding coordinates of the Fourier transform, u and v, are measured in wavelengths. The Fourier transform space is called the UV plane. The Fourier transform is cyclically symmetric about any line drawn through the center. This one, for example. Any point has its partner like this. Whenever we draw a point, we always draw its partner. A single point in the UV plane close to the center has a corresponding image that is a broad sinusoidal wave. A different point farther from the center has a corresponding image that is a narrower sinusoidal wave. If we select the UV point at a particular angle, the wave in its corresponding image has the same angle. These waves in the image are called Fourier components. Each UV point represents one Fourier component. When UV points are combined, the resulting image is the sum of the Fourier components. So, what does all this have to do with radio astronomy? We'll find out in the next section. Part 2, Aperture Synthesis. To make the best image, we must measure every point in the UV plane. A single radio antenna measures only the point at the center of the UV plane. As the size of the antenna increases, the point expands to a small circle. If we make the dish too big, with a single dish, coverage of the UV plane is limited. Two dishes operating as an interferometer measure a point in the UV plane away from the center. The resolution is the same as a single dish with a diameter equal to the length of the baseline. Each baseline gives 1 point in the UV plane. 3 dishes give 3 baselines and 3 UV points. To get better UV coverage, we can use an array of antennas. Here is an easy way to find the UV coverage of a given array. The Abro solar array has 5 antennas arranged like this. We select one antenna, move it to the center, and stamp it down. We select another antenna, move it to the center, and stamp it down. We repeat the process for all 5 antennas. These are the UV points measured with the array. When Abro measures a point source with this UV coverage, the image looks like this. The repetitions of the point source are called side lobes. Only the source in the center is the real one. The next section shows how to reduce these side lobes. Part 3, Rotational Synthesis. As the Earth rotates, the apparent size and shape of an array changes when viewed from a fixed point in space. Because of this, the UV coverage also changes. When ALMA measures a point source with this UV coverage over 8 hours, the image improves dramatically. This works nicely for a point source. Now let's try a more complicated image. Can you recognize the source? The next section will show how to get even more improvement. Part 4, Frequency Synthesis. Remember that the coordinates of the Fourier transform, u and v, are measured in wavelengths. The distance between two antennas can be measured in meters. However, it can also be measured in wavelengths. Say that we are observing at a frequency of 5 gigahertz. This corresponds to a wavelength of 6 centimeters. At this frequency, 300 meters is the same as 5,000 wavelengths, or 5 kilowavelengths. At 5 gigahertz, then, our 300-meter baseline is equivalent to a baseline of 5 kilowavelengths. To illustrate, let's draw a wave with each cycle representing 1 kilowavelength. Then 5 kilowavelengths is represented by 5 cycles. By tuning to different observing frequencies, a single physical baseline can have many different baseline lengths measured in kilowavelengths. Here, a 300-meter baseline observing at 4.2, 6.6, and 9.4 gigahertz is equivalent to 3 baselines of corresponding length. By observing at many frequencies, each point in the UV plane becomes a line of points. To image a rapidly changing source, such as a solar flare, we cannot wait 8 hours for the Earth to rotate. Instead, we must image with the instantaneous UV coverage available. For observing solar flares with the Owens Valley Solar Array, there is a great advantage in combining frequencies, as you can see. Combining data at many frequencies to improve imaging capability is called frequency synthesis. For slowly varying sources, such as a solar active region, we can combine frequency synthesis with rotational synthesis. When frequency synthesis and rotational synthesis are combined, so many UV points are measured that even a complex source is well defined. Part 5, Recap. For every image, there is a unique Fourier transform. The Fourier transform space is called the UV plane. Each UV point represents one Fourier component. Each baseline gives one point in the UV plane. As the Earth rotates, the UV coverage becomes more complete. This is called rotational synthesis. By tuning to different observing frequencies, a single physical baseline can have many different baseline lengths measured in kilowavelengths. By observing at many frequencies, each point in the UV plane becomes a line of points. Combining data at many frequencies to improve imaging capability is called frequency synthesis. When frequency synthesis and rotational synthesis are combined, so many UV points are measured that even a complex source is well defined.